I introduce the next one, and then we'll... So the next speaker is Professor Diana Golodnitsky from Tel-Aviv University, and she will talk about advanced nanoparticle-size materials for 3D concentric on silicon microbatteries. Another fun with lithium batteries.
It's not fun, it's very
Please.
serious, perfect. Okay. I'm small. Okay, good morning, dear ladies and gentlemen. The main issues which I would like to address very briefly in my talk are as following. What is the rationale behind the development of electrochemical power sources? What are the advantages and benefits of the three-dimensional microbatteries as compared to conventional planar battery design? And what are the achievements of our group in the electrochemical synthesis of active battery materials? The idea of wireless sensor networks has acquired a great deal of attention and progressed from concept to the commercial reality in the past decade. The scope of sub-centimeter microsensors is very wide, and this slide highlights the enormous potential they offer in the defense, environmental, home, medical, and commercial fields of application. For instance, the given imaging microcapsule endoscope for the small intestine makes during 10 hours of activation time something about 60,000 of images. It is obvious that this endoscope necessitates while miniature in size by high capacity power source. For the defense applications, the microsensors can be simply deployed in unfriendly environment, and they start to be operated by the solar cells coupled with rechargeable batteries. The capacity of the rechargeable batteries should be about 10 milliampere hour per square centimeter, and these batteries must deliver the pulse currents of about 10 milliampere, up to 100 milliampere. And there is no battery that can meet these very severe requirements. Inasmuch as these smart microelectronic devices continue to shrink and incorporate more and more complex functions, a high integration level of the micro power source with typically on silicon fabricated device is essential. As a consequence, conventional battery technologies are not so attractive as their miniaturization becomes highly problematic. Another issue, but not less important, is safety. Liquid electrolytes, which are used in commercial batteries, should be replaced by solid, hybrid, or gel polymer electrolytes, particularly for in vivo applications. The recently developed all-solid-state planar battery structures require typically relatively large battery footprints, and this makes them irrelevant for the microsystem applications. What is required is an entirely new class of microbatteries with peak-specific powers much higher than those of commercial batteries and specific energy values many times those of the existing capacitors. In order to achieve these goals, firstly, we have to overcome the limitations of low surface area of active battery materials per footprint of the battery. And to solve this problem, one of the ways is to use the three-dimensional microbattery architectures. Moving into a third direction invokes the simple principle of the geometrical area gain. This is followed by the increase of the surface area gain and volume gain of the active battery materials, and all these factors are associated with the increase of battery capacity and battery power capability. The most obvious approach to achieve a significant geometrical area gain is to replace the continuous substrate by a perforated one with high aspect ratio microchannels. The three-dimensional thin-film concentric microbattery, which is currently under development in our group, has a typical sandwich-like battery structure with successive layers of current collector, here it is, cathode, hybrid polymer electrolyte membrane, and anode. In the case that diameter of the microchannel is 50 micron, the interhole spacing is something about 10 micron, and the thickness of the substrate is 0.5 millimeter, the geometrical area gain is 23. By this is meant that we have more than 20,000 microbattery units per 1 square centimeter footprint of the battery. This slide summarizes the technological process as a whole, and I would like to emphasize at this point that this thin-film three-dimensional concentric microbattery, which was fabricated both on perforated silicon and glass capillary arrays plates, was fabricated by using solely the wet chemistry and electrochemistry methods. From these planar and cross-sectional ACM images, you can see that the thin layers of nickel current collector or gold current collector are continuous and coat all the available surfaces of the substrate. The next battery layer is the cathode. Inasmuch as many microsystems used for the environmental control or for defense purposes are operated by a couple with solar cells, their average voltage is around 2 volts. And now our first attempt has been made to prepare, with the use of electrochemistry, the thin film chalcogenic type cathode. From the ACM images at the bottom, one can see that the layer inside the microchannels is continuous, and the morphology of the deposits is very similar inside the layer and on the planar surface. The evidence of the formation of the hybrid polymer electrolyte membrane, which conformally follows all the previous battery layers, can be seen in the following ACM images. With the membrane, the sequential spin coating and vacuum steps, or sometimes centrifuging methods, were used to fill in the lithiated graphite-based anode material in the remaining cavity of the microchannel. And here you can see the upper ACM view of the polished structure. The full semi-three-dimensional concentric microbattery showed stable electrochemical behavior and low degradation rate. However, the sloping character of the charge-discharge curves is disadvantageous for some applications. The second electrode material, which we started to develop in order to eliminate the sloping character of the curves, is copper sulfide. We used also electrodeposition to prepare thin copper sulfide films. We have found that increase of the deposition time and also current density is followed by peeling of the films from the substrate. However, simple modification of the electrolyte used for the deposition of this material by polyethylene imine or polyethylene glycol dimethyl ether additives not only changed the morphology of the deposits, but also enabled preparation of thick cathode films at the deposition rate 5 times that found for the pristine cathode. The modified copper sulfide deposits are predominantly constituted of plate-like or octahedral-shaped grains. The grains, in turn, are assemblages of small, closely packed nanocrystallites, the size of which was about 35 nanometers, as we determined using the XRD tests. The longer is the deposition, the larger are the grains, and many of the grains approach the size of 5 micrometers. The morphology of the semi-three-dimensional copper sulfide deposits inside the long and narrow microchannels is very similar to that obtained on the planar substrate. However, the size of the grains in this case didn't exceed 1 micron. Analysis of the high-resolution XPS spectra of the electrodeposited copper sulfide materials revealed that modified samples are enriched in high sulfur content compounds like cobalt. However, the high deposition rate films contain large amounts of sulfur-poor chalcocite. Increase of the deposition time restored the initial content of the cobalt, as you can see from this spectra and from the analysis shown at the bottom, and also reduced the surface oxidation. The next slide shows some results of the electrochemical testing of the planar lithium copper sulfide thin film batteries. A pronounced plateau at about 2.1 volt is detected in the discharge curves, and here you can see the number of the cycles the cell was tested. The pronounced plateau was detected in the cells which comprise modified cathode. However, the cells with a pristine cathode has some slope here, and the charge discharge curves are steeper. Furthermore, on prolonged cycling, there is a broadening of the dq over dV peaks of the planar cell with pristine cathode. This raised the possibility that some disordering may occur in the system on prolonged cycling. The opposite is true for the cell comprising modified cathode. At low current densities, the charge discharge curves of the semi-three-dimensional cell with modified copper sulfide cathode are relatively flat. The sloping character of the curves at high current, discharge current are caused by overvoltage, which in turn we relate to the high internal resistance of the semi-three-dimensional microbattery, in which the anode is applied only to the upper part of the battery and is absent inside the channels. The modified copper sulfide cathode, with its pulse peak power of 18.5 milliwatt per square centimeter, even in planar cell configuration, outperforms vanadium pentoxide, molybdenum oxysulfide, and iron oxysulfide cathodes, all of which are prepared by electrodeposition and are under development in our lab. The capacity of semi-three-dimensional microbattery with modified copper sulfide varies from 1 to 2.5 milliampere hours per square centimeter. This is in a good agreement with the thickness of the cathode, with its composition and morphology, and also with the area gain. In the case of semi-three-dimensional microbattery on silicon, the area gain was relatively low and equal only to 9. This cathode in the semi-three-dimensional configuration delivered something about 60 milliampere per square centimeter, and peak pulse power of this semi-three-dimensional cell was about 50 milliwatt per square centimeter. This is 5 times that of the full three-dimensional cell with molybdenum oxysulfide cathode fabricated on the substrate with area gain 23. We expect that the energy density of lithium-ion copper sulfide battery, I mean full three-dimensional concentric microbattery, with optimized nano-size electrode materials and area gain higher than 20, will be about 30 milliwatt hours per square centimeter. And the projected pulse power for this system will be something about 400 milliwatt per square centimeter. And the last slide that I want to show you in my presentation is the comparison of the performance characteristics of the most advanced thin film all-solid-state battery, which is manufactured by Infinite Solutions company. This battery has the extraordinary power capability, and not only at pulse current regime, but also during this constant discharge current. The value which were presented so far are about 13 to 17 milliwatt per square centimeter. And I can say, unfortunately, that these values are something about 3 times higher than the values achieved by our system so far. However, when the capacity of this state-of-the-art planar all-solid-state battery, the area of which, by the way, is 1 by 1 inch, when the capacity of this battery is doubled, the power drops by a factor of 60 to 80. In our non-optimized semi-three-dimensional microbattery, increase of the capacity by a factor of 5 is also followed by the decrease of the power capability. However, this decrease is only by a factor of 20 to 40. And at the final point, and as a consequence on this power to energy changes, I want to show you the last data. When we compare the power to energy ratio of the all-solid state-of-the-art, I'm sure this is state-of-the-art thin film battery, with our system, we can see that almost at the same capacity value of 200 microampere hours per square centimeter, the power to energy ratio of the planar battery is 0.3. And this is 16, and for our case, it is 16.5. This ratio is something about 1.5 order of magnitude lower than that achieved for the semi-three-dimensional microbattery with copper sulfide cathode. And the main conclusion of our work is the following. It is expected, and I think that it is not only expected, but experimentally proved now, that the three-dimensional battery architectures can break the classic battery compromise. And the three-dimensional batteries with optimized active electrode materials and electrolyte and high geometrical area gain will be able to provide both high energy density and power density. These batteries on the perforated substrates will be safer than conventional batteries, and this is due to the small partitions which separates every microbattery unit. And we expect that the optimization of the process will enable to prepare or to fabricate the batteries, the microbatteries, of the footprint less than 1 square centimeter and even few square millimeters, which will meet the requirements of microsystems applications. And at the end, I would like, first of all, to thank my co-authors and our former and our current PhD and master students who actually carried out all this really complicated experimental work. And thank you for your attention.
Thank you very much, Dina. Any questions? Please.
Not only that I didn't show it, I didn't like to see it. The problem that when you discharge the battery to the lower voltage region, you obtain a non-reversible lithium sulfide. And while we really achieved much better performance with modified electrolytes, it is still impossible to ensure complete reversibility of this material. Therefore, we charge it in the narrow voltage window. And this is actually our goal, to work in this window.
Thank you. We have to move on. Dina, thank you very much.